Many people have watched a falling star, often called a shooting star, when I was younger. I honestly thought they were real stars falling from the sky. Just like the way I once believed in Santa Claus, but later I discovered something surprising: they aren't actually stars at all. While looking up into the sparkling darkness of the night sky, I realized that another meteoroid was once again attempting to punch through Earth's atmosphere. This happens all the time. Every single day, millions of small cosmic objects rush toward our planet daily. In reality, this is nothing particularly unusual. So despite how strange the phrase might sound, real falling stars actually do exist in space. So buckle up, everyone. Once again, we are heading into the depths of space. Meet Myra, also known as Omicron Ceti. This enormous star has a diameter about 700 times larger than our Sun. It is an even more fascinating and mysterious object than Betelgeuse, which we discussed in the previous episode. The earliest reference to this star dates back to Hipparchus around 134 BC, and later it was mentioned by Chinese astronomers of the year 1017. However, its truly unusual behavior was discovered only much later. Pastor and astronomer David Fabricius actually discovered this remarkable star the morning of August 13, 1596. At the time, he was simply observing the planet Mercury. More precisely, he was trying to measure the angular distance between Mercury and a nearby star that appeared to shine with a magnitude of about 3 within the constellation Cetus. Interestingly, he had never seen this star before, and it did not appear on any star maps or celestial globes available at that time, of course. Astronomical charts in those days were not nearly as accurate as modern ones. So overlooking a relatively faint star was not uncommon. Fabricius continued to observe this strange object, and soon its brightness increased until it reached a magnitude of 2. By the end of August, it had become the brightest star in the entire constellation. But then something strange happened. During September, brightness began to fade. And by mid-October, the star had completely vanished. Convinced he had witnessed a new star, Fabricius eventually stopped observing it. Yet 13 years later, on February 15, 1609, he was astonished to see the mysterious star again. To be fair, astronomer Johann Bayer had actually noticed it earlier in 1603. He included it in his famous star atlas, although he did not yet realize its unusual properties. At that time, the star had reached a brightness of roughly magnitude 4. Over the following decades, astronomers around the world began carefully observing Omicron Ceti. For example, the Polish astronomer Jan Hevelius, who studied it between 1659 and 1682, gave the star the name Myra. The word comes from Latin and means wonderful or astonishing, and honestly, the name suits it perfectly. Most of the time, that star is so dim that even small amateur telescopes struggle to detect it. Yet at certain moments, due to its unusual nature, it suddenly becomes the brightest star in the constellation Cetus. These moments are known as brightness peaks. After that, the star fades again until it becomes almost invisible. Then the entire process repeats itself again and again. By the middle of the 17th century, scientists finally realized that this strange object belonged to a new category of variable stars. These stars change brightness over very long periods, with extremely large variations. Simply put, Myra is a star whose brightness constantly changes, although not in a perfectly regular pattern. For those unfamiliar with the term, the brightness of a star refers to its apparent stellar magnitude. In simple terms, how bright it appears to us on the astronomical scale. Smaller numbers actually represent brighter objects. Myra's brightness can increase to magnitude 2, where it becomes the brightest star in its constellation. As mentioned earlier, its behavior is not perfectly predictable. Both the timing and the intensity of its brightness can vary significantly. At one point, Omicron said he shifted from magnitude 9 to magnitude 5, and then dimmed again on another occasion. It faded to magnitude 10 before suddenly surging to its maximum brightness of magnitude 2. Clearly, the fluctuations in its luminosity are enormous. But what exactly does this mean? At its faintest, the luminosity of an array roughly comparable to our own sun, or sometimes even slightly weaker. However, at its brightest, Myra can outshine the sun by about 700 times, and occasionally be as much as 1,500 times. The explanation lies in the nature of red giant stars. When red giants pulsate, the temperature of their surface changes dramatically. This affects the optical properties of the star's atmosphere. As the temperature rises, various chemical compounds break apart, making the atmosphere more transparent. Additionally, hot masses of hydrogen erupt into the star's atmosphere during peak brightness, further increasing its luminosity. At the moment, this is the most widely accepted explanation for the remarkable variations observed in Myra, but there is still more to the story. In 1919, scientists discovered that a second spectrum was superimposed on Myra's light. This spectrum belonged to an extremely hot white star. A few years later, astronomers confirmed that a small companion star orbits very close to Myra. This hot companion is a white dwarf known as Myra B. Interestingly, this smaller star is actually feeding the material from its giant neighbor. Myra B completes one orbit around Myra Avery for 100 years, which means since the time of Fabricius, it has completed only a single full orbit. The average distance between Myra and the orbit of the dwarf is around 70 astronomical units. About 70 times the distance between Earth and the Sun. What makes this system even more fascinating is that the small white dwarf also experiences changes in brightness. However, these changes occur for completely different reasons. Myra B possesses an accretion gas, through which it interacts with the main star, pulling stellar material from its massive companion. Because the flow of this material is uneven, the brightness of the dwarf also fluctuates. Its magnitude ranges between 12 and roughly 9.5. Studying brightness changes in stars like this requires enormous astronomical effort. Just imagine, to calculate the full range of brightness variations over a period of 13 years. Scientists must analyze every fluctuation that occurs during that entire time, and some of these changes can happen within minutes. Now we arrive at one final remarkable discovery: the Galaxy Evolution Explorer, also known as GALEX, is an ultraviolet space telescope launched into orbit in 2003. Using GALEX, astronomers discovered a massive stream of material being stripped away from Myra. Similar to the tail of a comet, this enormous tail extends roughly 13 light-years. To put that into perspective, the distance between our sun and the nearest star is only about 4 light-years. So this stellar tail is truly gigantic. Most stars in our galaxy move slowly around the galactic center, traveling at roughly the same speed as the surrounding interstellar gas. Myra, however, is racing through this gas cloud at about 130 kilometers per second. Because of this speed, the material expelled by the star is blown backward, forming a long tail of compressed gas. Calculations suggest that every 10 years, Myra ejects a mass roughly equal to the mass of Earth. To create a tail this large, the process must have continued for at least 30,000 years. Seeing such a phenomenon up close will be truly incredible. Unfortunately, to witness it directly, one would probably need to be a god. A huge bulging structure can also be seen in front of the staring images captured by the Galaxy telescope. This region represents a shock wave. It is similar to the wave formed at the front of a boat as it cuts through water. Or the shock wave in front of a bullet moving faster than sound. Here, matter expelled from the star collides directly with particles of interstellar gas. And with that, our story comes to an end for today. To conclude, astronomers have already discovered more than 46,000 variable stars within the Milky Way, and around 10,000 more in other galaxies, and this is only the beginning, because new ones continue to be discovered every year. If you enjoyed this story, feel free to like or dislike the video. Subscribe to the channel and share it with your friends. See you again next time.